Good afternoon, class. We are looking at exam 2 review, chapter 3, differentiation rules, covering from 3.1 to 3.8. The first part covering from 3.1 to 3.3, 3.1, derivatives of polynomials and exponential functions. 3.2, the product and quotient rules. 3.3, derivatives of trigonometric functions. And then we continue with more. Again, I want to remind you, when we take the exam, you take the exam on your own, then there's a pledge that says, I pledge on my honor that I will neither give nor receive unauthorized assistance, and so on. Okay. Now, differentiation, starting with the definition, dy dx is the limit of delta y over delta x as delta x approaches you. Or f prime of x is the limit of f of x plus h minus f of x over h as h approaches you. So we know that, and now we are going to make it easy by using formulas. For example, the derivative of x is 1. The derivative of c times f of x, the c comes out, it's a constant. The derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x, meaning the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. The following limits are useful. The limit of sine theta over theta as theta approaches 0 equals 1. The limit of cosine theta minus 1 over theta as theta approaches 0 is equal to 0. Couple of definitions for E. E is a number such that the limit of 1 plus 1 over n to the power of n as n approaches infinity. Also, E is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. So we mentioned the derivative of a constant. We have the derivative of a constant is 0. The derivative of x to the power of n, this is called the power rule, is nx to the power of n minus 1. The derivative of kx is k, where k is a number, is a constant. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tan is secant squared. The derivative of cotangent x is minus cosecant squared. The derivative of secant x is secant x times tan x. And the derivative of cosecant x is minus cosecant x cotangent x. So I'm giving you the synopsis of the differentiation formulas. And of course, we're going to put a bunch of time into it to master them. Now, a couple of important formulas besides those that have been mentioned. This is the product rule. This is the quotient rule. Fg prime, that means if you want to take the derivative of f times g, you get f prime g plus g prime f. And the quotient rule, fg prime is f prime g minus g prime f over g squared. This is the shorthand notation I use. It makes it very easy to memorize. Power rule, again, we repeat it. And if instead of x, you have a function to the power of n, you use the extended power rule using the chain rule. The derivative of g of x to the power of n becomes n g of x to the power of n minus 1 g prime of x. E to the power of x is an interesting function. The derivative is itself. Therefore, if it's e to the power of kx, again, it's itself times k. If it's e to the power of g of x, you want to differentiate, it's itself times g prime. If it's b to the power of f of x, which means the base is no longer e, is itself times ln b. That is by the logarithmic properties, and f times f prime of x, and this is by the chain rule. And again, we're going to elaborate on this as we come across them. This is the chain rule. F of g means f of g of x. So if you want to differentiate it, f prime, so y prime is f of g prime is f prime of g of x, g prime of x, or dy dx is dy du dx. So, and again, we'll see them with more details shortly. The derivative of natural log is 1 over x. So if it's ln of u is 1 over u du dx. If it's ln of g of x is 1 over gx, g of x, g prime of x, and so on. And these are inverse trigonometric functions. For example, the derivative of sine inverse is 1 over square root of 1 minus x squared. And the derivative of cosine inverse is the same thing with the negative in front of it. The derivative of tan inverse is 1 over 1 plus x squared. And the derivative of cotangent inverse is negative 1 over 1 plus x squared. The derivative of secant inverse of x is 1 over x squared minus 1. The derivative of cosecant inverse is then negative of that. So that's the synopsis of what we see as the formulas. Now what we are going to do, we are going to actually work them out with some examples to make some sense out of it. First and foremost, we're going to start with the power rule, the derivative of x to the power of n, x to the power of n minus 1. So if that is the case, 1000, which is the exponent, sits in front, and then x to the power of 1000 minus 1, which makes it 1000 x to the power of 999. You want to take the derivative of 3r squared. Please understand this is the product of 3 and r squared. So if you want to differentiate y prime is 3 times, now you take the derivative of r squared, 2r to the power of 2 minus 1 according to the power rule, and becomes 6r. Now what I want to add is this. You can write y prime. You can write dy dr. dy dr is Leibniz's notation. It is also telling you what is the independent variable. So ddr of 3r squared is 6r. This is the notation. Finally, for this page, we are going to take the derivative of f of x, which contains 1, 2, 3, 4, 5, 6 terms. And so we go one by one. First, this is 8 x to the power of 7. Then 12 times, this gives you 5 x to the power of 4. So 5 times 12, 60 x to the power of 4. Negative 4 times 4, negative 16 x cubed. Positive 10 times 3, 30 x squared. Again, we are using the power rule. Minus 6x, just like this one, becomes minus 6. And 5, like this one, becomes 0. So minus 6. And that's the final answer, everybody. Pretty straightforward. All right. Now, if we want to do the math, we are going to distribute first, and we're going to change the square root of x to x to the power 1/2. So I have put some exponential rules reminding you of what you're supposed to know. For example, right now it's square root of x. We should know it's x to the power of 1/2. The reason I do that because I want to use the power rule. So we're going to change this to x to the power of 1/2. And then I'm going to distribute. When I distribute, notice x has the exponent 1 when you don't write it. So according to this formula, you have to add the exponent. So this one has the exponent 1. This one has the exponent 1/2. When you multiply them, 1 1/2 or 3 halves would be the new exponent. This is 5x minus 2. And the reason we put it in this form, because now it's ready to use the power rule. So this becomes 3 halves, x to the power of 1/2, plus 5, and of course any constant is 0. And x to the power of 1/2 is square root of x. We put it in the same format we received it. Two x to the power of 5 over 9, x to the power of 9 is f of x. We want to differentiate that. And to do so, we're going to put it in a format that the power rule is in order. So first and foremost, x to the power of 5, x to the power of 9. If you look at the quotient rule, it's a to the power of m over a to the power of n is a to the power of m minus n. So this is x to the power of 5 minus 9. So 2 over 9, x to the power of minus 4. 5 minus 9. So according to the power rule, 2 over 9 times negative 4 x to the power of negative 4 minus 1. So this is negative 8 over 9. And this is x to the power minus 5. And according to the negative exponential rules here, if you have a negative exponent, you can take it down, make it positive. If it's negative down there, bring it up. So up, take it down, make it positive, negative 8 over 9 x to the power of 5. What is the derivative of pi squared? The purpose of this question is just to make sure you recognize this as a number. If it's pi squared, e 1.5, negative 8 makes no difference. You're dealing with a constant, everybody. The answer is 0. What about f of x equals 2, the fifth root of x to the power of 4? We are going to use this formula. And we're going to write this part as x to the power of 4 over 5. So 2x to the power of 4 over 5. Why are we doing that? We are getting it ready for the power rule. So 2 times 4 over 5, x to the power of 4 over 5 minus 1, according to the power rule. So obviously this is 8 over 5. 8 over 5. Then x to the power of 4 over 5 minus 1. Negative 1 over 5. So this goes down, becomes x to the power of positive 1 over 5, or the fifth root of x. All right. We want to differentiate the product of two functions. Now, I want to use the product rule. And in fact, notice I said do not simplify, because I want to emphasize the first step, which is the calculus step. Okay. And so having said that, okay, I can even distribute and there's no need for a product rule. But I want to mention that when you do the product rule, if I'm doing the product rule, I'm going to call this the f function, and I'm going to call this the g function. And I'm going to go with the shorthand notation. From the memory, I would write the formula f prime g plus g prime f. And so f prime is 4x cubed minus 6x squared times g. Just write the blue one. Plus g prime. This gives you 6x. This gives you minus 5 times f, the first function. And again, notice I said do not simplify. Of course, there are a few more steps to put them together. Why is it that I then want you to simplify? I wanted to emphasize the importance of the one and only calculus step. Okay, everybody, calculus. So this was a warm-up example. Let's do another warm-up example. We noticed that the function y is x squared times sine x. I put a raised dot to emphasize it's a product of x squared, which I'm going to call it f, and sine x, which I'm going to call it the g function. And so I would do that. Then I would write this formula again next to it and just follow that. So I need f prime g. So f prime is 2x times g sine x plus g prime. The derivative of sine is cosine times f, the first function, which is x squared. And I just rewrite it by bringing this in front, because if you don't, one may be under the assumption this is x cubed, which is not true. X squared is not part of the argument of cosine. It sits in front. And the final answer, y prime is 2x sine x plus x squared cosine x, can't be further simplified, and you're done. If h of x is x e to the power of x, find h prime of x. This is the product of x and e to the power of x. So we're going to call x the function f of x and e to the power of x the function g of x. So there are two functions that you're multiplying. And so we're going to use the product rule on that. F prime is 1 times g, which is e to the power of x, plus g prime, the derivative of e to the power of x is itself, times f, which is x. And so we're done with calculus. We're going to factor the e to the power of x out. We get e to the power of x times 1 plus x. And that's it. What about h double prime of x? What does it mean, h double prime of x? Higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function y prime equals f prime of x. Therefore, you can take the derivative of f prime of x referred to as the second derivative of f of x, f double prime, or f with the uh, exponent 2 in the parentheses. This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Using the prime notation for derivatives would eventually become somewhat chaotic. Use the numerical notation f, and then in the parentheses n, take the nth derivative to denote the nth derivative of f of x. It makes it easier that way. Okay. And so having said that, now we want to differentiate this. We are going to call this f and this g. So according to what I have here now, the f function, f of x is e to the power of x, the parentheses, the entire parentheses 1 plus x is the g function. And again, I'm going to use the product rule on that. Okay. So if I want to differentiate again, I need f from time the derivative of e to the power of x, of course, is itself, times g, the parentheses 1 plus x, or x plus 1 makes no difference, plus g prime, the derivative of the parentheses is just 1, because 1 gives you 0, x gives you 1. So 1 times f, which is e to the power of x. And I hope you notice that if I factor the e to the power of x out, this gives me x plus 1, this gives me plus 1, they add up to x plus 2. In other words, h double prime would be e to the power of x times x plus 2. I hope it's clear to everybody. So pretty straightforward. h of t is the fourth root of t minus 4 e to the power of t minus cosine t over 2, and we want to differentiate this. So to do so, I want to make sure we understand what we are dealing with. I'm going to change this to t to the power of 1/4 because we want to make it ready for the power rule. This is fine. This is fine too. But just in case, I'm going to rewrite it as negative 1/2 cosine t. So everybody can see it's cosine times some number. Okay. The number happened to be negative 1/2. So that's why I like to rewrite it in this fashion. Okay. And now let's differentiate term by term. The first one is 1/4 t to the power of 1/4 minus 1. Minus 4 e to the power of t is itself because the derivative of e to the power of x is itself. And remember, x is the independent variable. In this case, is t. So minus 4 e to the power of t, that doesn't change. Now, this one, I want to make sure we understand. It's negative 1/2 times cosine t. So negative 1/2 times the derivative of cosine, which is negative sine. So negative 1/2 times negative sine t. Now, this one is negative 3/4, which means we bring it down and we make it t to the power of positive 3/4, or the fourth root of the t cube, minus 4 e to the power of t. These two, the product is positive sine t over 2. First of all, I put that in the same format as this one, the same format as this one. So 1/4, the fourth root of t cubed, with the minus 4 e to the power of t plus sine t over 2.
You cut out, Professor.
I'm sorry. Okay, we're going to move on. I guess everybody can hear me, right?
Yeah.
Okay. So we're going to continue. We are going to go to the next example. So we want to find the limit, part A, limit of sine 3x sine 5x over x squared as x approaches 0. And reminding everybody of a couple of important limits. For now, we're going to use those limits to get to the answer. So limit of sine theta over theta as theta approaches 0 is 1. So we want to use that. And I want to emphasize, or the second one, cos the limit of cosine theta minus 1 over theta as theta approaches 0 is equal to 0. What it means, this is the argument of sine, must be identical to the denominator and must be identical to this variable in order to become 1. So the argument of sine in this case, and in this case the cosine, the argument of cosine, you want to be careful, you can't change them. So having said that, if you look at this piece, it has an argument of 3x. You can't do anything about that. You can't change that. And this guy has an argument 5x. So I want to be very clear as to what's going on, okay? Now, how do we deal with that? Very simple. We are going to cut the x squared into two pieces, x and x. Okay. We are not changing anything except we are cutting this into two pieces. Now, this argument can't change. This argument can't change either. So if I want all of them to be identical, I got to change this to 3. So how do I change to 3? Well, I can put a 3 here and 3 up here. This, if this is 5x, I can't change it. What can I do? I can put a 5 down and 5 up. Remember, this is a fraction bar. Okay, so let's do that. So I'm going to throw in a 3 at the top and the bottom, and 5 at the top and the bottom. Now, if you look at this piece only, okay, this 3x is the same. This 3 I can take out. This one, this 5x the same as 5. I can take the 5 out. And since x is approaching 0, so is 3x, so is 5x. So take a look at what I do. Number one, I want you to look at this one. This piece, I took the 3 out. This piece, and I'm making up two limits. This piece, I'm taking the 5 out. But this x, I change it to 3x. For this one, I change it to 5x. Why is that? Because if x is approaching 0, so is 3x, so is 5x, so is 10x. So why am I changing it to 3x here? Because I want them to have these three identical. I want them to have these three identical, so I must change it. And now each piece goes to 1, and the answer is 3 times 5 equals 50. Okay, so that's using the fact that the limit of sine theta over theta as theta approaches is 0 equals 1. All right, we are going to move on with this piece. The limit of cosine theta minus 1 over sine theta as theta approaches 0. It's none of those, but there's a trick involved. We recognize this one if it had a denominator theta. The same thing here. Let's divide the top and the bottom by theta. Let's separate them into two different limits, the top and the bottom. And now this piece, according to this one, is 0, and the bottom, according to this one, must be 1. 0 over 1 is equal to 0. The limit of cosecant x sine of sine x as x approaches 0. We know cosecant can be replaced by 1 over sine. So we're going to replace this by 1 over sine x. So we put sine x underneath. So cosecant x is 1 over sine x. Also, note that if x is approaching 0, so is sine x. And that's important to understand. Because we need to make sure that the following are identical. This part you can't change. This is the argument of sine. You have to make sure the denominator and this one are the same. So if you let sine x be theta, then limit of sine theta over theta as theta approaches 0 is given, and you know it's equal to 1. So that's a proof. In essence, you're changing sine x in all three cases to theta. You can even say that if you want. You can say let theta be sine x. Okay. What do we do here? Very simple. You notice that we have this to work with, and we can't change the argument. The argument of sign, it's important to understand this can't be changed. Okay? You can't touch that. So if you can't touch that, you try to manipulate the rest of them to make it look like that. Okay? And that's exactly what we are going to do. Which means we're going to make this one x squared and we want to make this one x squared. How do we do that? Well, I can multiply, this is a fraction. I can multiply the top and the bottom by x. When I do that, this becomes x squared. This x, I can take it out as a different limit of x as x approaches 0. And here's what I do. This part, everybody, this part, I use this one for it. The rest of it, remember, this is x squared, right? And because x is approaching 0, because x is approaching 0, so is x squared. So now this one, all those three are identical. So this is, according to that, equal to 1. And you can let theta represent x squared. And of course, limit of x as x approaches 0 is 0. 0 times 1 becomes 0. It's pretty straightforward, everybody. All right. Let's go with the quotient rule. F over g, that means f of x over g of x. You want to differentiate, you get f prime g minus g prime f over g squared. By the way, some of you may have seen this formula before in a slightly different order. The reason I like this order, because if you look at the product rule, you use exactly the same thing. You change the plus to minus. It makes it very easy to memorize that. So having said that, this is the f function, this is the g function, everybody. And I'm using the same f and g as I use for the product. So having said that, what is f prime? 4x cubed with the minus 6x squared times g times the bottom, the blue function, minus g prime, the derivative of the bottom is 6x minus 5 times f, the numerator, x to the power 4 minus 2x cubed minus 7, over g squared. Just put the denominator inside the parentheses and square it, and you're done. It's that simple, everybody. Again, notice I said do not simplify, because this is the only calculus step. You need a few more steps to finish this. This is not a finished job, okay? All right, differentiate. Do we need to use a quotient rule? That's really important for everybody to understand. We need to know the quotient rule and we need to use it when we must, on the one hand. On the other hand, if you don't have to use it and you use the quotient rule, you probably have a hard time finishing it off. And the answer is absolutely not. You don't need to, because this is one fraction, which is 10. This is the second one, which is minus 7x. And the answer is simply f prime of x equals minus 7. You don't have to do much. So algebra will help speed up the process, and that's extremely important, everybody. We want to differentiate y equals 1 plus sine x over x plus cosine x. And obviously, we are going to use the quotient rule. So we're going to call the top function as f of x and the bottom as g of x. So f of x is 1 plus sine x, g of x is x plus cosine x. And we're going to go with that formula. So we need f prime, which is simply cosine x. The derivative of sine is cosine x. Remember, 1 gives you 0. Times g, which is x plus cosine x. So f prime g minus g prime. The derivative of the bottom is 1. And then cosine gives you negative sine. So 1 minus sine x. And times f, the top function is 1 plus sine x. And finally, you put the denominator, you don't do anything. You just put it in a parentheses and square that. Let me put an asterisk to it because I want to emphasize this is it. You're done with calculus. Now, the rest of them would be your algebraic steps, maybe knowledge of trigonometry, and that's what's going to happen. So first and foremost, notice this is a minus b, a plus b, which has the product of a squared minus b squared. So this is 1 minus sine squared. So the product of these two x cosine x, the product of these two cosine squared, and the product of these two 1 minus sine squared. Notice the denominator is not touched. So what happens is that, what about 1 minus sine squared? Remember Pythagorean identities from trigonometry. Sine squared plus cosine squared equals 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. So if you look at the first one, you should therefore recognize the variation of that. 1 minus sine squared is the same as cosine squared. These two cancel each other. And the numerator is left with x cosine x. And therefore y prime is x cosine x over x plus cosine x, quantity squared, and we are done. The derivative of trigonometric functions were mentioned. And one of them was that the derivative of tan x is secant squared x. So let's prove that. The derivative of tan x is secant squared. And so reminding everyone that tan x is sine x over cosine x. In fact, reminding everyone that tan x is sine x over cosine x over 1 over cotangent x. Cotangent x is cosine over sine over 1 over tangent. Secant is 1 over cosine, and cosecant is 1 over sine. So now, the reason we write it as a sine over cosine, because we are going to use the quotient rule, and we're going to write f over g. So we are going to use this one, everybody. So f prime, the derivative of the top, the sine is cosine, times g, the derivative, the bottom is simply cosine, minus g prime, the derivative of cosine is negative sine, times the top f, which is sine, and you just write the bottom and square it. So you're looking at cosine squared plus sine squared. That's one of those Pythagorean identities. The numerator, they add up to 1 over cosine squared x. So if 1 over cosine is secant x, then 1 over cosine squared must be secant squared x. And that's the proof. The derivative of tan x is secant squared x. That's what we wanted to prove. Let's prove the derivative of secant x is secant x tan x. We have mentioned that the derivative of secant x is secant x tan x. Let's see how we prove that. Again, bear in mind that y is secant x that you are going to differentiate, and we said secant x is 1 over cosine x. And we are going to use a quotient rule on that. Again, f over g, where f is 1, g is cosine, and we are using this quotient rule. So f prime, the derivative is 0 times g, which is cosine x, minus g prime, the derivative is negative sine x, times f, which is simply 1, over the bottom, cosine x and square it. So cosine squared x. And this is the only calculus step. As you can see, this goes to 0. This becomes positive sine x. So sine over cosine squared, as you recall in trigonometry, sometimes you have to go with certain methodologies to prove identities. You're going to write this as 1 over cosine times sine over cosine. 1 over cosine, secant x, sine over cosine, tan x. And we just proved the derivative of secant x is secant x tan x. I highly recommend you try to prove the derivative of cotangent x is negative cosecant squared. The derivative of cosecant is negative cosecant x cotangent x in the same manner. Y equals 1 minus secant x over tan x. We want to differentiate. And again, we write it as f over g, which means we are going to use the quotient rule again. So f prime g minus g prime f over g squared. So the derivative of the top 1 gives you 0, negative secant x gives you negative secant x tan x, times g times tan x, minus g prime, the derivative of tan x is secant squared, so minus secant squared, times f, so parentheses 1 minus secant x, and you just write the bottom and square it, tan squared x. Again, done with calculus. We use our algebraic techniques, trigonometric information to finish the job. So what do we do? This is negative secant x tan squared. This one is negative secant squared x when you distribute, and this is positive secant cubed. So the numerator, we simplified as such, and we notice there is a common factor of secant x. So if I take the secant out, this gives me negative tangent squared. This gives me negative secant x, and this gives me positive secant squared x. So we take the secant x out. You get this. One of those Pythagorean identities was 1 plus tan squared is secant squared, which means if I move this, I get secant squared minus tan squared equals 1. Look at this one, and look at this one. The two add up to 1, replace them, and there's nothing else we can simplify any further. However, in trigonometry, sometimes you write everything as a function of sine and cosine, okay? So that's another way of approaching it, and if need be, finishing it. So if you were asked to do so. Find the points for which the tangent lines are horizontal. Recall, to get to the tangent lines, you need to find the slope of tangent lines. To find the slope of tangent lines, you have to differentiate. So first, let's differentiate this. So f prime is 3x squared minus 6x. And then they should represent the slope of horizontal lines, and the slope of any horizontal line is 0. Because of that, you set it equal to 0 and you solve. To solve this, obviously, we're going to factor the common factor of 3x out. So x is either 0 or 2. And it's important to understand the meaning of it. Those represent two different points. So if I put the 0 here, obviously I get 5. So 0, comma 5. That's very straightforward. What happens if I put the 2? Then I get 2 cubed minus 3 times 2 squared plus 5. 8 minus 12 plus 5 is 1. So the last pair, the second pair is 2, comma 1.